Okay, let's dive into a rigorous deconstruction of LLM inference mechanics. Today, we're analyzing a really consequential reality of modern AI architectures. We're going to uncover exactly why a clever algorithmic trick, one that's used to slash computation, silently shifts the entire bottleneck straight to your GPU's memory bus. If you've ever wondered why state-of-the-art models suffer such massive latency degradation as context windows grow, well, you're in exactly the right place for this explainer.
Here is our agenda for today. We'll start with hardware axioms and the roofline model, move into the algorithmic baseline and its O(n)³ disaster, and then introduce the KV cache. After that, we'll look at the systemic trade-off known as the memory bandwidth tax, touch on some state-of-the-art interventions, and wrap up with a deep dive into TurboQuant.
All right, Section 1, Hardware Axioms and the Roofline Model.
10 trillion. Modern deep learning GPUs are capable of executing over 10 trillion arithmetic operations every single second. That scale of computation is just staggering. But here's the fundamental catch we have to deal with. Silicon absolutely cannot operate on data it doesn't physically possess. It requires a massive, continuous stream of data pulled from the GPU's main memory, the VRAM, just to prevent those incredibly fast compute cores from sitting idle.
This exact dynamic introduces what we call the roofline model, which is really the ultimate lens for understanding hardware performance bounds. Throughput here is governed by arithmetic intensity. That's just a fancy way of describing the ratio of math operations to bytes transferred. High arithmetic intensity, you're compute bound, limited only by the silicon's clock speed. Low arithmetic intensity, you're severely memory bound. You're bottlenecked entirely by memory bandwidth, just endlessly waiting for data to traverse the bus.
Think of the GPU's compute chip like a massive shipyard, and the memory bandwidth as the delivery truck supplying it. LLM inference actually sits deep in the memory-bound regime, so the blazing fast shipyard is constantly starving, just waiting for the delivery truck to arrive from VRAM with the necessary model weights. The compute chip itself isn't the bottleneck at all. It's the data transit.
Moving on to Section 2, the algorithmic baseline and the O(n)³ disaster. Let's examine exactly why naive transformer inference creates a literal computational impossibility. In a naive loop, generating a new word requires broadcasting a query, key, and value. But to establish context, the model actually has to reread and recompute the attention matrix for every single prior token from scratch. And because attention mechanisms scale quadratically, recomputing across an expanding sequence results in catastrophic O(n)³ scaling. That's a cubic explosion in compute time.
Operationally, it's like taking meeting minutes by re-interviewing every single attendee from the very beginning every single time someone new walks into the room. For 10 people, it's tedious. But for a 2,000-word context window, it's completely paralyzing. This compounding waste is mathematically accurate, sure, but it's practically impossible to run at scale.
Section 3. Enter the KV cache.
To solve this quadratic disaster, engineers introduced a foundational architectural intervention. By simply caching the calculated key and value vectors of previous tokens, we completely stop the mathematical madness. Instead of re-interviewing everyone, we maintain a running notebook. When a new token is generated, we just flip to a blank page and add the new entry. Pulling from memory rather than recalculating slashes our workload from cubic right down to manageable quadratic scaling.
So the KV cache effectively trades compute for memory by storing past attention states. And every single production LLM inference system relies on this exact technique to maintain interactive generation speeds at extended context lengths. It's truly the absolute backbone of AI usability today.
But Section 4 brings us to the systemic trade-off, the memory bandwidth tax.
Architectural heroes always exact a toll, right? And applying our roofline model reveals the true paradox of the KV cache. By eliminating recomputation, we saved massive amounts of arithmetic. However, by storing gigabytes of token states in VRAM that must be fetched for every single generation step, we've handed the delivery truck an impossibly massive payload. The entire cache must be streamed through the compute chip for every new word. We have totally plummeted our arithmetic intensity, pushing inference to the absolute extreme of the memory-bound regime.
This is the core college-level concept to really lock in today. We cured a software bottleneck by dropping the arithmetic operations, but our I/O data load spiked massively as a result. Because the ratio of flops to bytes plummeted, the final hardware outcome is a starving GPU. The cores finish their math almost instantly, and then they just sit entirely idle, waiting for the memory bus to deliver the massive KV cache. We essentially fix the software by breaking the hardware.
Let's look at Section 5, State-of-the-Art Interventions.
To live with this necessary evil, the AI community has engineered a rigorous family of techniques. These interventions attempt to either shrink the truck's payload or pack it with much higher density. For instance, grouped query attention and multi-query attention literally shrink the cache footprint by forcing multiple query heads to share key-value pairs. Quantization increases density by downcasting weights from 16-bit floats to 8-bit or 4-bit integers. Meanwhile, page detention tackles VRAM fragmentation right at the OS level. Really, every single technique here is just a desperate attempt to push that arithmetic intensity back up the roofline.
Which brings us to Section 6, the TurboQuant Deep Dive.
Making the cache denser through quantization sounds great, but it introduces a subtle, highly destructive data loss problem that requires an advanced mathematical intervention. When you map attention vectors onto a constrained 4-bit integer grid, spiky vectors cause catastrophic precision loss. See, a typical vector contains one massive outlier magnitude and many really subtle values. To capture the massive spike without overflowing, the quantization grid has to stretch so wide that the smaller, nuanced relational numbers are literally rounded down to absolute zero. The outlier completely dominates the dynamic range, and it erases critical context.
Think of standard quantization like having one massively overstuffed suitcase, that's your outlier, and 7 completely empty ones. The memory bus still has to haul all 8, wasting precious bandwidth on zeroed-out data. TurboQuant solves this beautifully by applying a randomized orthogonal rotation matrix to the vector before quantization. This mathematical rotation perfectly smears that massive spike evenly across all dimensions. So now you have 8 evenly packed suitcases utilizing 100% of your bandwidth.
The workflow here is highly elegant. You simply rotate the vector to distribute the magnitude, quantize it safely into a dense 4-bit grid without zeroing out those small components, and then cache it. During generation, you read the dense cache, dequantize, and apply the inverse rotation. This fundamentally optimizes our data density without altering the core transformer architecture, successfully clawing back our lost arithmetic intensity.
Finally, Section 7, Conclusion. Let's distill the ultimate reality of large language model optimization. There's a saying in optimization circles, always ask, but what happened to the truck? If you only measure flop counts and ignore the memory bandwidth tax, the latency of your state-of-the-art GPU is going to be completely baffling to you. The KV cache solves an algorithmic nightmare, yes, but it does so by handing the exact same problem directly to the physical memory bus.
So, I leave you with this final thought. To genuinely push AI infrastructure forward, where should our true focus lie? What breakthroughs are we going to unlock when we finally stop optimizing solely for silicon arithmetic speed and start designing AI architectures built entirely around memory bandwidth? Thanks for exploring the true mechanics of inference with me today.